Everybody loves to spend time outside at the beach, but too much time in the sun will leave your skin burned and damaged. Two of the major sources of this damage to the skin are UVA and UVB wavelengths of solar radiation. The application of sunscreen helps to protect the skin from damage by absorbing these harmful rays and preventing them from hitting the skin. Current recommendations state to reapply sunscreen about every 2 hours to maintain a safe level of protection. Well-applied sunscreen will have an area density of about 2 milligrams per square centimeter. There are 5 active ingredients in a typical SPF 55 sunscreen. Oxybenzone is responsible for absorbing UVB radiation, while avobenzone is mainly responsible for absorbing UVA radiation. The other ingredients are support molecules, which help to slow the degradation of the absorber to reduce the rate of their consumption. Purification and degradation of sunscreen represents a conservation of mass problem. The mass of active ingredients from the sunscreen put into the system is consumed by the reaction between the ingredients and the ultraviolet light. This makes the system dynamic as the accumulation of active ingredients is changing as they are consumed by the reaction. Assuming the body starts with the sunscreen already applied before exposure to the sun, the system would be closed as no mass enters or exits the system, only energy in the form of solar radiation. To solve this problem, we must be able to make a few assumptions. First, we are assuming that a person always applies the recommended amount of sunscreen to their skin at an area density of about 2 milligrams per square centimeter. Second, we must assume that the energy of the incoming photons, E equals hv, remains constant through the course of the reaction. Next, we are assuming that the UV absorbers, oxybenzone and avobenzone, do not interact or affect one another's photoreactions. And finally, we must assume that there will be no sunscreen loss to other factors such as being washed away by water or skin absorption.
So our goal is to find the time it takes for 75% of the sunscreen to remain. To do that, we have our general equation, T at 75 equals 0.25. The units would be in grams over grams per second. The degradation rate is the rate at which the sunscreen degrades, and it's in number of molecules degraded per photon. So now our equation, T of 75 equals 0.25 times the concentration of our sunscreen times the percentage of each species divided by the molecular weight of each species times Avogadro's number divided by the degradation rate of each species times the amount of energy generated by the sun and divided by the amount of energy per photon. For our concentration, we found our sunscreen to be 2 milligrams per centimeter squared, and the energy of each photon is determined by hc over the wavelength. Now, h is Planck's constant, c is the speed of light, and we determined our wavelength to be 340 nanometers.
We start out with oxybenzone. We know that the recommended application amount is 2 milligrams per centimeter squared, which we convert to grams. From there, we multiply by the percent abundance in sunscreen, which is 6%. After dividing by its molecular weight of 228.24 grams per mole, we can multiply by Avogadro's number to get the amount of molecules per square centimeter. By dividing by oxybenzone's quantum yield value of 1.3 times 10 to the negative fourth molecules degraded per photon absorbed, we find that there are 2.43 times 10 to the 21st photons absorbed per centimeter squared. Factoring in the energy from the sun at 100 milliwatts per square centimeter, assuming that energy is constant, we divide by the energy of UV light given off at a constant wavelength of 340 nanometers and find the amount to be 1.8 times 10 to the 17th photons per centimeter squared times seconds. Dividing the first amount by the latter, we solve for how many seconds it takes for oxybenzone to degrade. We multiply this number by 0.25 as we believe sunscreen should be reapplied once 75% of the protection has been degraded. Using the same process with avobenzone's percent abundance, molecular weight, and quantum yield of degradation, we find the time for reapplication is 6.697 minutes. We realize this is an absurdly short amount of time to reapply sunscreen, but then we also take into account that octocrylene, another active ingredient in sunscreen, stabilizes the photodegradation of avobenzone by a factor of 6, which pushes reapplication time to about 40 minutes.
The application of conservation of mass principles show that a significant amount of the active ingredients in sunscreen will degrade within the first 40 minutes of sun exposure. Therefore, we recommend you should reapply after about the first 30 minutes of sun exposure in order to protect yourself from harmful ultraviolet rays.